Welcome to the K105 class in the Electrical Engineering Technology Department. My name is Pete Solari. I will be the instructor for this semester, and I want to welcome all of you. We have actually 12 students registered for the class, which is the maximum for the class, so that's great. Just to go over some business things, please find the syllabus in Blackboard. You need to go over that. There's a lot of information there about how we run the class. The schedule is in the back, so you need to see that. And it sure will answer a lot of questions about, again, how we do things. When homework is due, the collaborative work, I think I just want to note that will occur after each video on Monday and Thursday, and then I need it turned in by 10 p.m. that evening. So again, all in the syllabus. If you look at that, I'm sure that'll answer your questions. So today we're going to talk about three things. We're going to talk about engineering notation, Ohm's law, and the resistor color code. So let's get to it. If I write a number such as this one, 2.12, sorry about that, 2 times 10 to the 5th, in scientific notation, in engineering notation, it would be 212 times 10 to the 3rd. So in scientific notation, you'll always have one digit in front of the decimal point, and so that can be a 1 to a 9. In engineering notation, there would be 3 digits, or up to 3 digits, I should say. It would be 1 to 999, and you can see the powers change because of where the decimal point is. Right? In the case of engineering, you move it 2 more places to the right, and so that reduces the power of 10. So let me just draw another example here. Clear the screen here. So if I draw a transmitter, and we abbreviate that by the word MTR. That's a transmitter. And that's transmitting power of 750,000 watts, effective radiated power. That would be a TV station or a radio station, and the waves that go through the air, electromagnetic waves, and then we have a receiver on the other end with an antenna and a speaker, and an observer. So, so we have 750,000 watts transmitted power, and it's attenuated by the air. And at the other end, we receive a signal that's 0.00001 watts. So if we draw that, or write that, I should say, in scientific notation, it would be So 750,000 watts would be 7.5 times 10 to the 5th watts, and the attenuated signal would be 1 times 10 to the minus 8 watts. So so this is scientific notation. And in engineering notation, I know I'm kind of writing it on me here. Engineering, it would be 750 times 10 to the 3 which equals 750 kilowatts. And on the receive side, we could write that as 10 to the minus 8th would be scientific. We could write that as engineering as 10 times 10 to the minus 9th watts, which equals 10 nanowatts. I wanted to show you how to convert this number on the Casio. So we had, we're going to use our received power of 0.0000001 watts, and if it equals, you'll see that it's 1 times 10 to the 8th down in the lower right hand corner. So that's scientific notation, and then you press the ENG key, and now you've got 10 times 10 to the minus 9th, which is in engineering notation. The next thing we want to talk about is prefixes. So if we have 10 to the power of 12, that's tera with a capital T. If we have 10 to the 9th power, that's giga with a capital G. If we have 10 to the 6th power, that's M, mega, capital M. 10 to the 3rd power is kilo, a small k. And then 10 to the 0 is unity, is 1. And that is, there's no name for that. Then there's 10 to the minus 3 is milli, that's a small m, lowercase. We have, I guess I'm getting in the way here now again. We have 10 to the minus 6th is micro with it's a U, a mu from the Greek alphabet. And then we have 10 to the minus 9 is nano. And then we have 10 to the minus 12th is pico. And all of these are in the textbook, and you really need to commit those to memory. So let's talk about some examples of of this notation. Now let's let's look at an example of prefixes. If I have a computer memory that's 8,000,000,000,000 bytes, that can be written in engineering notation as 8 times 10 to the 9th. That's a 10 there. Excuse this pen. I'm going to get a finer pen for next time. And that becomes 8 gigabytes, GB. Let's take a human hair. That would be 0.00075 meters. And if we want to write this in scientific notation, let me get a different color here. We count back 1, 2, 3, 4, 5 places to the decimal point. So then that becomes 75 times 10 to the minus 6th. Because remember, we had this number has to be between 1 and 999 meters, which equals 75 micrometers. We're now moving on to chapter 2, and we're going to talk about Ohm's law, which is a relationship between voltage, current, and resistance. So if I draw, I say voltage, we call that E, a big E, which is electromagnetic. Force. And then current. We call I, capital I, and resistance. Which we call capital R. And we there's a relationship between the three of them, and we kind of draw it this way: E, I, R. So if you want to solve for E, you cover up the E, and that equals I times R. If you want to solve for current, I, you cover up current. Cover up the I there, and it's E over R. And if you want to solve for R, you cover up the R, and it's E divided by I. In this demo, we have a battery, a light emitting diode, an LED, and a resistor. just as we do in the circuit. And what we're going to show here is that the battery has a plus side on it, and if we put the diode in the correct direction, it lights the light, just like that. But if we reverse it, the light does not light, and that's because it's a diode, and that allows current only to flow in one direction. I draw a schematic of a simple circuit. We'll start with a voltage source, a battery. And there's a plus side and a minus side of a battery. The long bar is the plus side, and the small bar is the minus. We don't have to label a minus because, or the plus for that matter, because it's kind of assumed by that symbol with the long bar that it's the plus side of the battery. Okay, let's continue the schematic here. We'll add a resistor, and then in this case a light emitting diode. Which would be an LED. Resistor. Remember, it's an R. And the battery, we'll call that a 9-volt battery at this point. That's the battery. Okay. So current, we'll draw the current through this circuit, which flows around the circuit from plus to minus. So we'll symbolize it like this, see? With an I. That's the current. Flows from plus to minus. Current is defined as electrons moving in a wire, and it's they're also, the electrons are called the unit of measure is called coulombs. Okay, and coulombs per second equals amperes. Also called amps. It's very analogous to, or I should say there are analogies to electric circuits. For instance, if you have a hydraulic circuit, the battery, just change the color, okay, is the same as a pump in a hydraulic circuit. Electrons, which are flowing through a wire, become water in the pipe. Water in the pipe. A resistor actually becomes resistance of the pipe, and that can be caused by the skin effect of the pipe, the diameter of the pipe. You know, a larger pipe would have less resistance than a smaller diameter one, as there would be friction between the water flowing in the pipe and the pipe itself. Now let's draw another circuit. We'll start with a DC power supply. Another way of drawing one. And we'll add a switch. An ammeter with an A in the circle. A resistor. add that back to our negative side of the power supply. So this is a resistor R, and we'll put a voltmeter across the resistor. So this is a DC. Probably I'm in the way again here. Power supply. And we have current flowing in the loop. This is an ammeter. This is a voltmeter. Okay. So it's kind of very important to note that the current flows through the ammeter, but not the voltmeter. If we lift the voltmeter wire, and then let's see if this eraser works. If I do this, yeah, look at that. How about that? If I lift that line, let's go back to if I lift that line, nothing changes in the circuit. The current still flows through the ammeter and the resistor. The voltage is measured across the circuit. I think that's the important thing to note here. So let's talk about Ohm's law. If we draw a simple circuit again, this time we'll use an AC source, which is we'll call it 120 volts AC. Connect it through a switch. Resistor. Back to the negative side. Well, it's actually not a negative side because it's alternating current. The voltage alternates, so it goes from plus to minus. So there is no plus or minus designation on that power supply. And we have a current that we're trying to calculate. So we know there's a current in there. We don't know what it is though, right? Question mark. And we know the voltage is 120 volts, and we'll call the resistor 8 ohms. 8 ohms. With the omega sign. That's the ohms sign. So we want to calculate I. We know E, voltage, and we know resistance R. So if you remember our little table, E over I R, and we want to calculate I, we cover up I, and we say I equals E over R equal to 120 volts over 8 ohms. And that equals 15 amperes, or amps. So in the other case, we have we have another circuit. Basically it's the same circuit, but we're going to change the parameters of the circuit. We're going to make the voltage 4,160 volts AC, alternating current. We're going to say the current in the circuit equals 80 amps, and the resistance is unknown. So we're going to calculate the value of the resistance, again using our little formula E divided by I times R. We cover up the R this time, so R becomes E over I, and that is equal to 4160 divided by 80 amps, and that equals 52 ohms. Before we get into resistor color codes, I wanted to talk about resistor types. There are various types of resistors based on the composition of the resistor, how they're made, that is. Some are carbon, made of carbon. Some are wire wound. The wattage varies. You can have a very low wattage resistor. This one right here, if you can see it, is a 1/8 watt resistor, which is very common, used on circuit boards and electronics. Some are big, heavy power resistors that are wire wound and dissipate a lot of heat. They can they're sometimes thousands of watts. They might be used in a power station, for instance, to dump power off of the grid. And there can be multiple resistors on a single chip. They call them chip resistors. Now with the small integrated circuit chips we have today, surface mount, you can have as many as 20 or more resistors in a single package. For pull-up purposes or inline resistors, there's just a lot of different types, and you can peruse that at your will. So now we can, and there's also variable resistors. That would be like a volume control. You know, they're metal with a shaft, and inside there's a wiper and either a wire coil or even carbon. So as you turn that, the resistance changes. And some are 3-terminal, as in the case of a potentiometer, where the resistance goes down on one side with respect to the center. Remember, 3-terminal, and then it goes up on the other side. So they're used a lot in a lot of things. Radios, a lot of electronics have variable resistors of some sort in them. Now let's go to color codes. I'm going to kick this over. By the way, this is found on DigiKey. Whoop! I think we just changed something here. Let's go back here. Okay, there we go. Okay, so this is found on DigiKey, and so what we're going to do is, I have a resistor here. It's an 1/8 watt, and we're going to measure the resistance. I'm going to set this meter up here. Hopefully it'll stay. Okay, and if you can see the display there, I'm going to measure this. Let me just kick back here a minute so I can see it. Yep, okay. And hang on one second here. Not getting a good. Whoop. Good contact between my meter and. Okay, so it's 0824 kilo ohms. So that's 824 ohms. So now what we'll do is we'll go to DigiKey here. Just set this meter aside. We'll go to DigiKey, and we'll put in the color of the bands, which is gray. Second band is red. Third band is brown. And the color, the tolerance band is gold, which is 5%. Okay, so there's our resistance by the bands, 820 ohms at 5%. Now let's go back. So, we had on our resistor, the first band was gray, equals 8. The second band was red, equals 2. And the third band was brown, equals times 10 to the first power. So the third band is always the multiplier, and as you saw in the chart, each color will be another power of 10. Okay, just as brown is the number 1, if it were in another band, it becomes the power 10 to 1, 10 to the first. If you had a red third band, it would be 100 times 10 squared, which is 100. So you would multiply the first two bands. In other words, 82 times 100, and that'd be 8,200 ohms. The fourth band is the tolerance band, and it's gold, and that is plus or minus 5%. So we can see that the bands say plus or minus 5% tolerance of 824 ohms, 820 ohms, and we had 824 on the meter, so that is within tolerance. So if we had a, let's just say we had a, let's see if I got room right here, 47 ohm resistor at 5% tolerance, which means the resistor would the range of the resistor would go from 444.65 to 49.35. Okay, and that, in other words, you can multiply 47 times 0.95, and it would go to 40. It would go to 40, or you multiply times 47 times 1.05 will give you 49.35. So that would be the tolerance range of that resistor. The other thing I just wanted to mention before we leave for today about resistors is that I'll ask you if a resistor is or is not in tolerance, but would not require you to memorize the color codes. There'll be a chart instead in the tests and exams. So that ends it for today. We'll see you next time.